So thanks for having me. It's a pleasure and an honor to be here. I'll be talking to you about spin dynamics and out of equilibrium superconductors. This work was, excuse me, doesn't seem to be, yeah, there we go. So this work was done in collaboration with a large number of people, notably Marko Kuzmanovic, PhD student, and Marko Arprilli, head of the group. Marko Kuzmanovic will be presenting a poster right after this on part of this work, presenting more details than I'll be able to give you, so you should go and look at his poster. And also Freek Massé, who is the most recent permanent addition to our group, will be presenting a poster on a different topic on an STM for noise measurements that he has been building over the past couple of years, and you should also go and look at his poster. Okay, so I'm going to start with some general remarks on excitations in superconductors and where the spin comes in, and then I'll move on to the main part of the talk on dynamics. So there are at least a couple of ways to represent quasi-particle populations in superconductors. So one way to do it is, of course, to draw the density of states and to color in the quasi-particles with some distribution function. So here, for example, you have the BCS density of states and then a electron-like quasi-particle up here and a hole-like quasi-particle here. It's the kind of thing that you can imagine happening with like Fermi direct distribution, for example. You can draw the exact same thing in this sort of diagram, where the axes are the quasi-particle energy and the electron energy. And this population is represented here in this way. So one way to think about it is that on the diagram on the left is just the diagram on the right, sort of cut in half and flipped over. So now these quasi-particles have a number of interesting properties, one of which is that the group velocity and therefore the diffusion constant is actually 0 at the gap edge, and then it rises to the normal diffusion constant or the Fermi velocity at high energies, and this will be important for some of the things I'm going to tell you later. The other thing which is interesting, has already been alluded to in the previous talk, is that there is a sort of back action of the quasi-particles on the condensate via the BCS gap equation. It's probably easier to see this in this approximate formula over here, which basically says that the more quasi-particles you've got, the smaller the superconducting gap. And then finally, it turns out that the charge of the quasi-particles is also 0 at the gap edge, and then it rises to the normal electron or the whole value at high energies. And as a consequence of this, and also as a consequence of the fact that quasi-particle number is not a conserved quantity in this system, it turns out that the charge and spin degrees of freedom are completely decoupled in the quasi-particle population in a superconductor, and they can be addressed separately. Okay, so non-equilibrium physics in quasi-particles and superconductors has been studied really extensively in the 70s and 80s. At the time, most of the devices were millimeter size, as you can see here, but the idea is basically similar to what I'm going to show you. Actually, was already shown in the other talk. You've got a superconductor. You're injecting quasi-particles from here, a normal electrode across a tunnel junction, and then you detect a non-local signal either with a normal superconducting probe, again, across a tunnel junction. And in this particular experiment, what was measured was the charge imbalance, which is to say a difference in chemical potential between the pairs, these data. So the spin imbalance length here was measured to be about 10 microns at 1.7 Tesla. And actually, in a very simple Drude model, this 10 microns corresponds very well to these 10 nanoseconds that we measured. But obviously, this is not the whole picture, and we'll come back to this towards the end of the talk.
Sorry, can I ask, in the 10 nanoseconds that you measured was still from a transport measurement, so it was not from an AC measurement?
Both. I'm not talking about AC measurements here, but it's in this PRB.
Okay, so yeah. Basically here actually you measure the length.
No, here we do a fit to this signal. This is the first paper. Yeah. But they agree very well. Both the DC measurement and the AC measurement agree. Yeah. So anyway, so as I said, I'll talk about some of these issues later, and for the moment, let me move on to the dynamics, and in particular, the quasi-particle spin resonance. So again, probably a reminder, when you do a spin resonance experiment, typically you have a magnetic moment. Here is the quasi-particle spin in an external static magnetic field. The spin aligns to this field over a time, which we call T1, and then you can supply a tickling magnetic field with microwaves which causes the magnetic moment to precess around the static field. Then if you look at essentially the power absorbed here as a function of magnetic field for a fixed excitation frequency, then you'll see a peak at the resonance field. And the width of this peak will give you T2, the coherence time of these precessions. So there are a couple of challenges associated with measuring this sort of thing in superconductors. The first being that the magnetic field is obviously inhomogeneous due to the Meissner effect. Well, it turns out that if you have thin films of the thicknesses that we have, the field can be homogeneous to less than 1.5%. You actually gain twice by reducing the thickness, because for one thing you go below the penetration depth, and for the other thing the penetration depth itself actually increases when you have a thinner sample due to the sigma term here. So this leads me to the second challenge, which is that typically, as you saw in some of yesterday's talks, these spin resonance experiments are done with really macroscopic samples in macroscopic cavities, and so we overcome this by using on-chip power detection. Okay, so we have two different on-chip power detection schemes. In both of them, here you have the superconductor and a magnetic field pointing in this direction. That's the external static magnetic field. And then you have the tickling magnetic field being provided by a small supercurrent which is flowing through the superconductor itself, like so. And then in the first power detection scheme, we measure the conductance across one of these tunnel barriers. So in this picture, actually, this electrode is useless. And then in the second scheme, we measure the supercurrent along across this length of the superconductor. Okay, so now let me convince you that these things are actually a good measure of microwave power. It's probably easiest to see this in the second case. So if you look at simply, oops, why is this not moving? Here we go. So if you look simply at the differential resistance as a function of current in this scheme, then you see a peak here at the critical current, and you can see that as a function of the RF power, the critical current is going down. This means that if you sit here, for example, at the red line, oops, if you sit at the red line here, clearly the greater the amount of RF power arriving here, the smaller will be the critical current, and vice versa. Now, it's a little bit more complicated for the other detection scheme, but it's essentially the same sort of thing. So here at 0 RF voltage, you have the two BCS peaks, which I showed you earlier. And then you see that when you increase the RF voltage or the RF power, these peaks split into two. So this is simply the phenomenon known as classical rectification. It's a fancy name for convolution of whatever signal you have with the histogram of a sine wave, which has two peaks at the edges, right? And so now if you sit up at a particular bias voltage, for example, this one, and then you look at how this evolves with RF voltage, you get something like this. And I think you'll agree that if you sit here and you look at the conductance, then basically this gives you some measure of how much RF voltage is arriving at your tunnel junction. Okay, so that's exactly what we do. We sit here and we look at the conductance, and if we're able to measure spin resonance, then we should see a signal which looks something like this. And this is indeed what we see. Conductance is a function of magnetic field for a fixed excitation frequency. Now, obviously, to check that this is actually what's going on, we can change the excitation frequency. And if we do that, we see something like this. And now if we take the peak positions as a function of magnetic field, we get a G factor which is more or less correct. And also the width of the peaks gives us the coherence time, which I was talking about. And that seems to be on the order of 100 picoseconds or so. Now, we've also checked this using the other method, because this is obviously the conductance across the tunnel barrier method. If we look at this, oops, not this one. Sorry, I'm having a whole trouble with these things. So if we look at the supercurrent as a function of magnetic field, again at a fixed frequency and power, we see in this graph here that the results, which are the thick lines, agree very well with the results from the previous method. So that's all well and good. We also did these measurements on samples which were slightly thinner. So this number which I gave you is for the 8.5 nanometer samples. And then when you reduce the thickness, the T2 actually goes down slightly. This corresponds to these squares over here. And so for the moment, we believe that, and I think on this at least I agree with the previous speaker, we believe that T1 is limited by inelastic electron-electron scattering, both because of the values and of the thickness dependence, and T2 is limited by Elliott-Jaffet spin-orbit scattering. And we have independently confirmed each of these times with microwave measurements, here with microwave measurement and here with an equilibrium measurement. I can talk about these things if you like later. Okay. So at the moment, what we're doing is looking at how spin influences the recombination dynamics of quasiparticles. Again, like most of these things, this topic has been studied really extensively in the 1970s and 80s with millimetric samples. And again, you recognize the superconductor. You inject current through one of the electrodes. The side view here you can see perhaps better. And then you look at what they call the excess current on another electrode. And at the time, the equations which were used to describe this sort of thing look something like this. So essentially, they couple the kinetic equations for the quasiparticles and for the phonons. Now, in our case, obviously, we have spin. We also have a delta which depends not only on space, but also on the injection current. We have a diffusion constant, which, as I showed you, depends on energy, also depends on space and the injection current. The injection density in our case, with respect to this case, is about 1,000 times higher, so we are way more out of equilibrium. And for us, because of the small size of the samples, the phonons are much less important. Okay, so to look at the recombination dynamics, we have samples which look like this. Again, very similar to what we've seen before, a superconductor, a normal metal injection junction. And the big difference here, of course, is that the detectors are now also superconductors. So the bar is 6 nanometers thick, and the detector junctions, detector electrodes are 8.5 nanometers of aluminum. Now, if we look at the conductance as a function of voltage at one of the detectors, we see something like this. So the conductance is a function of voltage. And obviously, one of the quantities that we can very easily extract from these data is, oh, come on, is the sum of the superconducting gaps of the two superconductors. And another quantity that we can extract from these data is the area under the low energy features, or equivalently, the plateau current in the I of V. And this, as it turns out, is essentially proportional to the number of quasiparticles that you have under your detector. So we'll look at each of these things in turn. Let's start with the superconducting gap as a function of the injection current at two different magnetic fields. Well, the first thing you'll notice is that for both magnetic fields, the delta actually goes down as a function of injection current. That's only to be expected. You remember that I said earlier that the more quasiparticles you have, the smaller the gap, so that's all well and good. And however, if you look at the low field and the high field traces, you see that the high field trace appears to go down more quickly, roughly around the region of the first Zeeman peak, which is highly suggestive. If you look at this as a function of space, then you see that this difference between the high and low fields is very apparent when the detector and the injector are very close together, and then after about half a micron or so, this thing has died out. Now let's take a closer look at one of these sets of traces, for example, at the 175 nanometer traces. So if you look at this as a function of magnetic field, you see something like this. And here I think it's much clearer that, let's ignore this peak for the moment, I'll come back to it later, that at low magnetic field, at a given injection current, at low injection current, there's hardly any movement at all of delta, whereas at high magnetic field, delta is moving quite quickly. This, in fact, is mirrored also in the other quantity we're looking at, which is the number of quasi-particles as a function of injection current. So at low field, again, very little movement, and then for the very same injection current at high magnetic field, you see that you have, several times more quasi-particles under the detector. Obviously, the quantity we're changing here is magnetic field, and you like to say that, okay, these things are coming from the Zeeman effect and therefore from spin. Obviously, also the magnetic field doesn't create only the Zeeman effect, because there's also an orbital field that comes in, even though our devices are extremely thin. Suffice it to say for now that we've checked this, and we're fairly convinced that this is spin-dependent recombination, and you can ask me about the control experiment during the question time. So now, obviously, the next question that we can ask is, okay, so these things look very similar to each other. Actually, this one just looks like a flip-over version of this thing. Do we simply have this sort of thing, which I showed you earlier, the greater the number of quasi-particles, the smaller the gap, or does this thing, in fact, have some spin dependence? So does n up and n down somehow come in here? So there are, one of the theoretical predictions out there, which has some fairly strong assumptions, claims that if you look at delta as a function of number of quasi-particles, then if the quasi-particles are unpolarized, you should get this sort of thing. And if the quasi-particles are polarized, you should get something which goes down much faster. So this is obviously quite intuitive or logical in some sense. You would think that if you have spinful quasi-particles, this should have a greater effect. And in fact, unfortunately, this is not at all what we see. So for, oops, what's wrong with this thing? So for different magnetic fields, everything seems to more or less fall on the same curve, and this is true. We've done this for 2 or 3 devices, and it gives the same thing every time. So unfortunately, for whatever reason, which for the moment we don't understand, there seems to be really no or minimal direct spin effect on the gap itself.
Charis, are you going to tell us what's happening very low either? The yellow curves?
Yes, so that's exactly what I'm going to do now. So in some devices, especially those where the injector detector distance is very, very short and there is a high transparency, we see this hat thing here, which corresponds to this signal on this side, actually. So what's going on here is that essentially you see that you're looking at delta at an extremely small injection current. You're putting almost nothing into your superconductor. For whatever reason, delta is coming down really quickly. And what we think is going on at the moment is probably that, remember I told you that the quasi-particles have essentially a diffusion constant of 0 at low energy. So what we think is going on is that, at low energies, you're injecting quasi-particles into the, just under the injector. They're not going anywhere because their diffusion constant is essentially 0. And also there's a kind of self-trapping phenomenon because they're not going anywhere to depress the gap locally, and then this acts as a kind of trap. So even though there are no quasi-particles practically at the detector, the gap at the detector is going to be decreased just because of the proximity to the injector. And that's what we think is going on. So obviously this is going to complicate the equations drastically, because now it means that Andreev processes also have to be taken into account. What I mean by this is that if you imagine that your quasi-particle sitting in the injector, then basically when you reach this boundary, you can bounce back again with an Andreev process and vice versa. So there's an Andreev trap, if you like, going on here. We tried to play with the various different kinds of equations without a huge amount of success. But anyway, the goal of all these equations is to try and figure out what's going on exactly at the detector, right? So this is the question at the detector, do we have something like this, or something else? So we decided to get a hold of the other end of stick and basically look at the detector signal and try to back engineer the distribution function from there. One thing we can say is that it's definitely not a thermal distribution. And a reason for that is that quite simply we look at the low energy features as a function of temperature. So this is increasing the fridge temperature. And then at the same time, we looked at the low energy features as a function of injection current, and you can see that the shape is not at all the same. So let's try to say now something more than just the fact that it's not thermal. So we had several different approaches to this. We tried to deconvolve the detector signal. We used a fit which had different Fs for the two different spins. This is inspired by this work. There's a slight error in the calculation, but the idea is essentially a right one maybe. And then there's also a spinless fit that we can do, which is basically adding these two things but saying we don't have any spin. We tried also to do an effective temperature fit, and we have some fairly strong assumptions, which we can come back to. And if you do that, you find that essentially any of the approaches will give you something that works more or less. This is the detector current and the detector voltage, except the one which assumes some effective temperature. And on the right are the distribution functions and the number of quasiparticles which we obtain from each of these methods. Okay, and here let me show you a movie that Marco made, showing these same quantities as a function of injection current. Ah, yeah, there we go. Yeah, so okay. Say again? So we can fit everything, all injection currents, we can fit the I of V, and you can see that when you cross the second Zeeman peak, the second spin band begins to become populated. Okay. So that's very nice. Okay, so there are some issues with this thing. One of the issues is that there are some quite strong assumptions, which is that the distribution is the same in the bar and the detector, for example, and it doesn't work for all samples quite as well as for this one. And so to get around some of these problems, we are in the process of making new samples at the moment, which will have a thicker injector to keep it at equilibrium, because that was an issue as well. We're now changing the detector. We're not using a pure superconductor anymore, but a superconductor with some spin orbit to remove the Zeeman splitting. And this seems to work very well, and we're also increasing the detector barrier. And so measurements will be forthcoming in a very short amount of time. So based on everything we know so far, what we think at the moment is that the distribution function is probably spin dependent, very close to the injector, within the spin flip length, sorry. And then it becomes spin dependent a little further from the injector, but it's certainly not thermal, and remains to be seen what exactly it is. And then very far from the injector after the inelastic electron-electron length, sorry, then you get equilibrium. So this is a summary of the main things I've talked about. Do I have 2 minutes or no? It's over.
Maybe 1.
1 minute, okay. So, so perspectives, obviously, we're very interested in thermoelectric effects and things like that. But also, one of the things we're thinking of doing is to overcome this limitation of the excitation by tunnel barriers. So essentially you see here that if you sit at this peak and you want to inject more quasiparticles, you can't really, because when you inject more quasiparticles, you go up in voltage, you change your energy, and you change the spin state of things that you inject. So in order to overcome this limitation, we're thinking of doing something, we started doing something like this, where we're trying to inject spins from the ferromagnetic precession of something like cobalt platinum and exciting this mechanically with a surface acoustic wave to keep this far away from the superconductor. And we have some preliminary results that look like this. This is a collaboration with Peter Leek. And so thank you for your attention. If you have any questions,